Thanks for giving me this opportunity to talk in here. This is the tentative plan of the 3 hours lecture. Well, but it all depends on a couple of factors. First, I noticed that most of you coming from condensed matter background, so probably you haven't seen superconducting qubits. In fact, you have the chance to actually see them today. So the first talk is a bit more interactive, meaning it would be going through lots of equation, maybe not getting to the whiteboard or blackboard exactly, but very close to it. So you may want to take notes. Although I shared my notes and these lectures as of a few days ago, I've been editing them. So I would ask them to upload them again as the whole thing ends again. There's minor edits in there. So if you want to print or something, you might wait for a few more days. But anyways, there are more articles we have done recently we can get into, but it all depends on how much question you ask. So I ask Esther very kindly to stay in the back so you guys can interrupt me asking questions. I didn't really particularly big fan of waiting for the questions to the end. So for her waiting back there for 1 hour, not to go in vain, you might start asking me questions. Okay, so let's get started. I think that's all I have to say. This timing is all tentative, depends on how much you interrupt. And the goal is not to get to these boring stories to the end, so you have to kind of ask questions, so we extend on it and all that. Yeah, I'm a bit jet lagged, so you might see long pauses between sentences and whatnot, but that's okay. But the point is making it more interactive is you don't fall asleep, I don't fall asleep. This is the group of the people who actually, my teammates, this is a pre-COVID picture. The current size of the team, as you could guess by the number of authors on the articles we write, is 3 times of this current size. This is the very pre-COVID picture, but that's the last time we got together. So I have this taken in a rooftop of Los Angeles office. So we are about 150 people in Southern California, mainly Santa Barbara. That's, if you don't know where Santa Barbara is a little north of Disneyland. And then we have in Bay Area, Munich, and all over the place. So the purpose of this talk, the first hour, so this is what we got. Okay, so 3:41. In 60 minutes, or maybe sooner, depending, we are going to understand what this is. I'm showing you an object and a Hamiltonian, and the goal is to connect these 2 pictures. The object I have, in fact, with my hand, and I'm going to pass it to you, and I'd like you to examine it very carefully. And there is a couple of reasons I'm passing it to you. Probably you haven't touched something like this before, but by that I mean don't touch it, but as that professor in UT Austin did it. I don't mention his name, but okay. But the point is that this is a giant atom. And the fact that it's a giant atom, you can see it with naked eyes. And you can see the macroscopic quantum degree of freedom. I mean, you don't need to take it home. You need a microwave sources. You need dilution refrigerator. So you would not be able to reproduce our experiments at home. But at least you can look at this component, and you can see qubit with your naked eyes. That's exactly nominal to this. So it's about 1 centimeter by 1 centimeter. There are 9 qubits at the center. And I'm showing you a zoom-in picture. It looks weird to you what it is. It's, in fact, nothing but pattern of aluminum, and we've painted in Photoshop so you know the functionality of the elements. So all you're going to look at it is a reflection of light from aluminum, 200 nanometer of aluminum on a silicon or sapphire substrate. And at the end of the first hour, we're going to try to understand why Bose-Hubbard is the Hamiltonian describing the interacting photons in this system. Yeah, we understand what this is soon. So let me pass this around. What else do I want to say on this? Well, okay, another reason I can show this without losing job is that this was done by a grad student many few years ago. So Google doesn't own this object intellectually, although the current qubits is nominally the same. This is the limit. You could go 1 dimension. As soon as you get to 2 dimensions, you have to figure out how to address the middle qubits, right? As soon as you have 9 qubits, there is the issue of middle qubits. So you make the flip chip. And then again, in fact, you can take a picture of it because there's one chip on top of another. You don't see anything of what we have done in between. So all those colorful pictures you see on the internet, is showing you nothing. Two chips that are kissing each other, and there's nothing that you can see. But this is 1D, so you can see the concept of how we lay out, how we arrive at Bose-Hubbard Hamiltonian. So there are 28 lines around here. You can count. And if you're curious or mathematician, these SMA wires here are the control to the terms of the Hamiltonian. So I would not talk much about our actual hardware here, but the sum before the Hamiltonian. So the sum HI means the terms to control a single qubit. So it takes 2 degrees of freedom to 2 wires to control a qubit. And J is to couple the coupling between them. That takes, again, n-1 degree of freedom there, and the nonlinearity come for free. But what I want to say is that to control qubits, it takes that many wires to control 9 qubits. And each wire, technically, if you care, I don't know, it costs about $1,000. So a very expensive way of writing Hamiltonians. So I would really appreciate if you spend time with it, take a picture with it, post it in whatever social media you do, whatever. I don't care. This is not any secret there. So the start point of the story is in 1960s or 70s. I don't know. I wasn't born. So So someone named Brian Josephson realized if you have 2 superconductors and you put them very close to each other, that Cooper pair can coherently tunnel between them, then you can get a constant current going between the 2. And the current phase, the magnitude of the current depends on the sign of the phase difference. This phase is the Ginsburg-Landau phase difference across the barrier. And this is how we make them these days. You put a layer of aluminum, and then you put an oxide. You don't see it. There's a 5 nanometer of oxide, and you put another layer of aluminum on top, and that's how you make the junctions. Also, Josephson's second relation tells you that if this phase, Ginsburg-Landau phase difference, changes, you get a voltage develop across them. So that's all we need to know to make qubits, essentially. So what it takes from there is that, well, because we know how conventional inductance are defined, so I'm just going to take a derivative, nothing fancy, derivative with respect to time, assuming phase is changing. But the phase change is given from the second equation. So you replace it, and you see the voltage is given by this relation. But if you compare it with the way that inductive is defined is the ratio of voltage divided by change of current. So if you compare these 2 relations with each other, what to expect, you can extract an effective or practical inductance, which is very distinct from the with making a spiral out of wire, in a sense that the phase difference here appear in the inductance relation. And it depends on, it gives you a very nonlinear inductance. And this becomes very technically important matter. In the notes, I said that this is only technicality. You can technically just cool down a wire and have a qubit. It's going to be very hard to manipulate that qubit, but technically, it's just provide the ease of manipulation and give you an opportunity to have large value of inductance over a small area of space. Since we're going to start driving Hamiltonian, remember the destination was to arrive at the Bose-Hubbard Hamiltonian. I want the energy term, so I'm going to integrate power over time. And again, I and V are all given up there, so I'm just going to put them in here and integrate cosine of phi, I guess. Yeah, d phi, it's even, I can do that. So you arrive at this famous cosine theta real cosine phi relation for the inductance energy of a Josephson junction. And that's become key on what we need. But let's go back to something which is simple harmonic and we can manipulate. So I refresh your mind on the mathematics we want to use in here, and then we simply replace it with this nonlinear relation I said. Let's say you have an LC oscillator, and again, we are going to define the current and the phase, the charge and noise, the phase are well defined up there. We just defined as the integral of voltage over from this point that we force it or we define it to be the 0 voltage. And it's a matter of convention to call one of them kinetic energy and one of them the well, for Josephson and then drawing analogy with mass spring is rather all for convenient. There is not much deep physics in there. So you can based on the phase at this point, or flux at that point, essentially, you can write kinetic and energy term, kinetic and potential terms, and you can write the Lagrangian for this system. That's all you need to arrive at, and that's really a way of doing lots of designs. In fact, when we design qubit, we start with this, and we engineering the parameters of this Lagrangian that we like to have. And from Lagrangian, getting the canonical parameters, and usually since, oh, but I forgot to say, when you go and take the look at the notes, if you have done it, apparently you didn't, you would see there are 10 questions at the end of it. I would be happy to answer questions while I'm here or even later. There are 10 homeworks I wrote, lots of hints to how to answer them. And during the talk, I provide hints on how to answer questions. OK, 8 questions. I would give you some hints to understand, because I really want you guys to become good qubit designers by the end of this talk. What else you could do is you just can check the Kirchhoff relation, just equations of motion. This is standard things to do. And you see it makes sense to you that, essentially this relation is saying that the sum of current going to the left and to the right from that node is 0. OK, nothing fancy. So the promised Hamiltonian arrives by just, again, standard classical mechanic tricks that you know. And well, OK, now I'm going to take a leap and introduce the quantization for the quantum, to get to quantum physics, and just a bunch of definitions just for convenient. And putting this together, you arrive at the, this is the Hamiltonian for the linear case. And all we are going to do is just to replace this. So let me just, for the continuity, we get 4e squared over 2c n operator, charge operator, plus some flux over 2 pi phi squared over 2l. And this is the flux operator. But what I have done in here, I just called this 4EC, nothing different for the capacitance part. And this one, again, all gets sucked into definition of EJ, but is also minus, if you remember from the first slide. And now we have cosine of phi operator. And 1 minus phi is squared over 2. You see the first term in the expansion gives you the harmonic potential. But the key point is that there are higher terms into the expansion of the cosine. The object that you're looking at, where is it? OK. It has these values. Again, is not very hard to come up femtofarad numbers of capacitance. That's the capacitance of the object. But getting that much of current and getting that much of induct associated with 9 nanohenry in such a tiny area of a space is a blessing that comes as a result of having a Josephson junction, in addition to nonlinearity. And then the rest is just a bunch of parameterization and a bunch of things to make you familiar to what you see in the literature. Well, if you want to, I keep saying nonlinearity. If I want to give you the number so you can live with it, is 4% nonlinearity. And soon I describe what does it mean. OK, again, just nothing, just playing with parameters and redefining the Hamiltonian for the transbond, which we really need to have. So the harmonic term, you can see, comes as a result of expanding the cosine. And again, probably you want to do the numerics, or at least we want to do the numerics in the lab. It's very frequent. So you think about raising and lowering operators, because that's how we know how to write matrices and do the work by truncating these operators. And that's how you can check. It depends when you're born. Some people, OK, I don't say born before which year. They would do perturbation theory, and then some people do numerics. But also here in the notes, I have something very simple. So you see this is not very mysterious. You write the raising and lowering operators, and you just phi and n is defined. You just write them, truncate them however you like. You just add them up with these things, and then I give you the convenient value for eta and natural frequency omega p, and then you just write a larger matrix, and then you ask for the diagonal eigenvalues of that matrix. That all goes into arriving at this celebrated picture. That it tells you that if you have a harmonic potential, which is this parabola, you get the energy levels, which are the dashed lines, uniform spacing. If you make a qubit, Josephson junction, you get the levels that are getting jammed and jammed together because you're now talking about a cosine potential. And for our case, for the qubits, we have probably about 12 to 14 level fits before they get closer and closer, and then the 15 would be free particles, sort of. So given the raising and lowering operator we defined, you see n squared gives you a minus a dagger squared. This one gives you also a minus a dagger. And there would be a fourth order term. So if you expand it, you can see it. That's why I wrote in here. So well, if you come here and write, cosine of phi, write it like this, 2 and then 4, you can see you arrive at this higher order term, and the rest, everything else can be packaged together as the harmonic oscillator. So the higher order term in the cosine giving you nonlinearity. So by now, I have shown to you that just playing with the terms and whatnot, you get these two first terms of the Bose-Hubbard Hamiltonian. So if you put lots of qubits together, this would be the Hamiltonian, yet they do not interact with each other. That's not very useful. Time to take questions. Crystal clear. That's what I want to know. So far we got to non-interacting case. So, but life demands these qubits to interact with each other. Again, I try to build your intuition by going over simple cases. Again, we're just going to put the nonlinearity aside. We're just going to figure out what we are doing by coupling two LC oscillator capacitively. That's extremely also trivial to make in the lab. You make a couple of islands and you put them next to each other. The geometry, the electric field that goes out the plane makes them to couple to each other, and that's kind of can be simplified in this thing. By now, you're all masters of writing Lagrangian, so close eyes, you can just quickly write the Lagrangian for the system. And what you're noticing that, the voltage difference across the capacitance is what gives its energy. And the voltage is a derivative of the flux, of the phase difference is the voltage. Hence, this is the new terms I wrote here. The rest is just a bunch of standard harmonic potential cases, right? So I want you to understand that, this is the kinetic terms of individual. This is the potential of individual. The only term I'm adding here is this C coupling, and the voltage difference, or the derivative of the flux difference across that is give you the interaction term. So a challenge in the lab is to make this CC value sizable. One bigger challenge in the lab is to make it 0 when you don't want them to be 0. And I can maybe explain, if you're interested, how we do that. OK. Again, don't go forward quickly. You just look at your equations of motion. You take derivative with respect to phi dot, time total derivative, and then you can see that the first relation tells you that you have done it correctly, that the sum of the current that emanating from this point is 0, and the sum of the three currents that emanating from this point is 0. So you're doing a good job. You can continue. And you can arrive at see the relation between charge degree of freedom and flux degree of freedom. Remember, we have to take off the derivatives, right, to write the Hamilton, to be able we have to know our canonical parameters, so we can write the Lagrangian of the system or Hamiltonian of the system. Sorry. Okay, so for the first time now we are looking at the Hamiltonian of the system. Let's take a look. again, standard things of the individual ones, and then you know this is not that scary. It just means harmonic potential and a bunch of higher terms. And the take-home message is that capacitive coupling leads to charge-charge coupling. And that is this term, which you should be able to trace where is that coming from, given what we have written down. Subtle point, important point, I don't know, you might face it in your life in a different context, is that these masses, let's call them masses, these individual capacitance also have been renormalized. So you probably have seen it in a different context, that now you have two oscillators together. If you write it in this format, even the kinetic terms the mass that enters them is renormalized. I'm sure it has different name in different fields, but there's nothing fancy except saying following correct. I don't want to, at least in this context, I don't want to give a deeper meaning to it than just playing with the math. It's not any extra step. It just follows from the math. Okay, so this is the case of two coupled systems, two coupled qubits. And we can move forward, because this I also want to tell about this a little bit for two reasons. A little more difficult to understand how to inductively couple, but also is important to say this because capacitance is all about geometry. You put the qubits together, they couple because the size of the size of the area cannot be negative. So you get area, you get capacitive coupling. You put them together, you get positive. You get them farther away from each other, you get another positive number, which is smaller, but it's always positive. It's just about size of the islands that you define as your qubits. However, inducting coupling, not as simple as I draw, a little more advanced version of it, can give you the opposite side. And combining this and the capacitance, you can now get zero. Zero is very important, because when your qubits do not interact, you don't want them to interact, you have to pass through zero very reliably, so you have a high fidelity gates. That was one of our efforts, which took a few years to figure out how to do reliably, and leading to high fidelity gates. Okay, but so in that sense, it makes sense to work out this example. Is a little more complicated, or there are several ways to think about it wrong. Maybe that's the correct way of saying it. Yeah, did I get it right? Maybe not. Okay, yeah, okay. These 5 fluxes are defined in terms of these inductance transformation matrix. And you put it again together, you arrive at the Lagrangian of the system. And again, now this time, okay, so I put the terms related to a simple harmonic together. And again, in this case, is the individual inductances that are normalized. And what you want to know from this exercise is that when you inductively couple, you get flux coupling.
What did you mean by zero, the mutual inductance?
No, I mean that the final coupling between the two qubits, you don't see it in here, but I'm just saying we can talk offline of how to mix and match inductive and capacitive coupling, so there is a tunable parameter which allow you to really get zero coupling between the qubits.
But is it tunable in situ or fabrication-wise tunable?
In situ.
Okay.
So you turn it on, turn it off on demand. Yeah.
If I understand correctly, that's basically when you get to the effective Hubbard model. If I understand correctly, that's just when you get to the effective model that looks like the Hubbard model, just the interaction term, you want to be able to have it vanish.
Exactly.
And you want to have this vanish when you want it, just to be able to basically have independent qubits.
Well, the best vanishing point is you go through zero. If something allows you to go negative, and it can be positive, according to Newton, must go through zero at some point. That's the key.
Thanks.
Yeah. Okay, take-home lesson. Capacitive coupling give you charge-charge coupling. Inductive coupling give you flux-flux coupling. I defined it. Didn't write it down. I defined the flux in terms of raising and lowering operator. I defined charge in terms of raising and lowering operator. We put it together. And if you don't give me a hard time, I would say, let's just focus on particle conserving, photon conserving. If you give me a hard time, I have to give the actual explanation. But so you see, you get 4 terms. I just wrote 2 terms, right? A dagger, I'm dropping. The official description is going to a rotating frame, has to do with actually what we measure, and then some rotating wave approximation. But let's just keep the particle conserving cases, make our life easy. And you see from the 4 terms that are in this expansion, I'm keeping 2 of them because they are particle number conserving. And usually the dynamics that we are dealing is that. And ta-da, this is the equation for Bose-Hubbard, as I promised. This was what they derived before, no complaint there, this one. And these terms are coming in here. OK, I have to take questions now. Yes?
Thanks. I just quickly wanted to ask, when you explained the inductance, what's it called? Induction coupling, did you lose on the way the cosine terms, or did you do something
No,
there?
I got lazy.
Okay.
I showed, yeah. Well, I was, OK. This is correct. This is a complete package. But if you want to really get to inductive coupling of qubits, it's not as simple as replacing these 2 elements. I have to add 2 more elements. And you have 6 quantum components, and I got lazy. I didn't want to write the Hamiltonian for that. It's a bit more complicated. I didn't write. I'm just giving you a hint on the on the part that most people get confused over, which is this one. So everybody can do the homeworks. But if you really want to inductively couple qubits, OK, you see what I did was cheating in here, right? I said, oh, let me draw this. I arrive at Lagrangian, or I could arrive at the Lagrangian. But just right before I arrive at Lagrangian, I say, I'm not going to write phi squared. I'm just going to write cosine of phi. It was a very shortcut I took. I'm showing you Hamiltonian for qubits, and I'm showing you different picture. As soon as you imagine these 2 objects are replaced by qubits, by Josephson junction, we are good to go. Unfortunately, this is not as simple as here. You cannot eliminate or replace them. You have to add those components. So I have confusing slides as a result.
Okay.
Yeah.
But yes, just to make sure, so then it is true that they appear, the phi coupling appears as
But also the phi coupling appears, yes.
as an argument, and then you, can you use that for?
You see, then there would be another node introduced and whatnot, but still the physics is there.
Okay.
The mathematics get a little uglier. Yeah.
Thanks.
Yeah. Sorry, this is a bit confusing. I keep jumping. I do half of the mathematics in linear case, and then I jump into nonlinear at the end. That's confusing. OK. Let's take a look. This is the, yes. Okay, hold on a sec.
Oh, sorry. Just because you're talking about these terms dropping out, and I know that you said that maybe it's a bit complicated, but and you kind of said particle conservation. It's just, I don't really see directly, because, this we kind of introduced these ladder operators later on, so it's kind of, is there direct reasoning to say that these terms actually drop, or?
Yeah, well, in the actual experiment, well, if I give you the physical reason, is that the measurement in the lab happens in the frame that rotates with a bare frequency of the qubits, more or less. That's just most convenient way of doing experiments. So now I have to take all this Hamiltonian to that rotating frame. So even if you don't drop these things, when you go there, they oscillate with twice frequency, and they get dropped over there. But I try to hand wave around it.
OK, that's good. Thank you.
Sure. These slides need some work. OK, we good? I'm sorry. All right. But also, much better than me that if you truncate these raising and lowering operators to confine yourself to qubits to only 2 levels, then you get these Pauli spin operators. So you can say we have XY model that we are dealing with. You can populate the higher levels if you want, but if you're really confined to the hardcore boson models, that's also possible. Okay, enough. Oh, what is that? Oh, surprise. These are what really we do in the, okay, so look at this here. Now you see how impossible it is to do. You have raising and lowering operators, and you have 5 coupled qubits, let's say. This become tensor product of however number of levels you want to go times identity on everything else, and this become a very complicated tensor product and whatnot. So 5 qubits, depending how far you go to this A and A dagger terminate, you, let's say, 3rd level, you get 3 to the 5, and it's really computationally hard. So do electrical engineering do what we do, or is that something? No, the very big shortcut we take in the lab before we embark on journey of doing Hamiltonians and whatnot is to really borrow from electrical engineering and look at the admittance matrix and impedance matrix and whatnot. And let me see what I have, right. So you have to write inductance matrix and capacitance matrix, and in the note I explain how to do that. And the effect of a large system of linear coupled oscillators can be solved, and then nonlinearity qubitness can be treated as a perturbation on top. So you can write this. I wrote it here, and the homeworks I wrote it for many other cases, and then simple relation tells you this. So there's no mystery about solving system of coupled linear oscillators, and that's a very good way of getting intuition of if your results is correct or not. And that's exactly in the limit of nonlinearity being 0. So it's more than a trick. It's a very big guideline on how to work and operate in the lab. Most of the simulation in the lab is just do this and assume there's nonlinearity. Yeah, that's how we do things. So now I want to tell you about what actually qubits are after all this mathematics and whatnot. We keep talking about 0, 1, 2 states of the qubits, and you can't believe how many people are confused over what they are. Okay, maybe if I give you the example of a standing wave in a pipe or tube or lambda over 4 resonator is sufficient enough for you to understand what's happening. There is a resonator. Resonator have modes, and each mode can have its own occupation. Let's say here is an example. First mode has two excitation in it. Third mode has 5 and whatnot. So this is a scenario, right? This is a very general scenario. However, when we make the qubit, the one mode frequency is far more accessible than anything else. And that's the famous 6 gigahertz that we work on. The other modes are much bigger one. And this mode happened because of the object we use. The lump element is a very good approximation for it, meaning that the one object in the resonator is doing the capacitive job, another good approximative capacitance, no need to think about as an inductance aspect of it, and the other one is the other way around. Not that this doesn't have capacitance or that doesn't have inductor, but this lump element approximation is a very good one, and it's really make life simpler. So we are only going to focus on this lump element mode, so-called, and we are able to put excitation on that. I'm not ever going to show you how this lump element mode look like, but you can imagine the lowest mode of a standing wave in a pipe or something. It's a good description for it. So we can go and populate as much as we want, and now comes the confusing language. This object, aluminum on sapphire, we call it qubit. Computer scientists call these 2 levels qubit. So when you do Bose-Hubbard on a qubit, is a recipe to get referees mad at you. But yeah, anyways, now you see what we call qubits. But also some notion of modes and this lump element, and that there's nothing fundamental about it. You can understand by going to the homework and so on, solving a couple of mass spring things, and then you can take the ratio of the masses or make this K to be very strong, so these two move together and whatnot, and I guided there how to do these kind of things. So you can develop an intuition for what this lump mode physics is about. There's nothing profound about it as far as I know. Okay, yeah, so questions. Okay, okay, I have 20 minutes to go, roughly on time. Okay. Okay, these are the questions that you see. I think I'm happy to answer them. Some are conceptual, some are demand you to do some perturbation expansion or not. So let's just summarize. So the capacitance of the qubit is this island of aluminum, which we just painted red in Photoshop, nothing there. So there's a strip of aluminum, and then there's a strip of nothing. This aluminum is separated. Everything you're saying, we call it ground plane, is to be sure that there is no voltage develops across the qubits, across the chip, and everything is at the same frequency. These funny objects you see in here is that coupling term, which gives you this coupling term, and now you know too much. I would have said that, okay, look, this goes from positive to negative, and we can set it to 0 and goes to 30 megahertz and all that. But now you know there's more into it. So now I can give you the secret sauce. These two have capacitance coupling to each other. They're islands. They're going to have positive capacitance. The ingenuity of the design of this is that it goes positive and negative, so there's a chance for compensation. So essentially, totally secret, we may need to take it out of the video, is that this is another qubit at 14 gigahertz. The others are 6 gigahertz qubits. So that's essentially, if you go and introduce that element, you will see how the whole things work together. These funny lines up there are the readout of the qubits. These are standard LC oscillator, and they have a very sharp frequency, let's say at 8 gigahertz. If the associated qubit to them is occupied, this 8 gigahertz goes to 8001 gigahertz, meaning 1 megahertz shifts. And we know that this meant to be at 8, so it's now at 1 megahertz shift, so this qubit must be occupied. You send the signal here, you take it out here, and each qubit has its own resonator. They are different lengths. If you could maybe notice by seeing these objects are not identical. They have different lengths. The length set the frequency, and I know, for instance, 7.5 meant to tell us what's happening at this qubit. So you look at this resonance frequency, and you see how much is shifted, tells you this is occupied or not. So in the quantum advantage experiment, we read all the qubits at the same time because each of them has its own signature resonator associated with them. So in one shot, you set a pulse at 8 gigahertz, pulse at 7.5, pulse at 7.8, blah, blah, blah. And then you look at them and their respective shifts. So in order of 1 microsecond, or maybe even 600 nanosecond, you know the states of the qubits. And you reset and start over again. Maybe I don't get a chance to say that later. We can repeat this procedure close to 10,000 times a second. OK, we are about to do physics for real now. Yes? So we have to, OK, yeah.
So you can control like these two couplings to them to cancel.
Yeah, right. So control lines, as I said, controlling a qubit on its Bloch sphere, it takes two wires. XY is one wire, Z is the other wire. And this one, by sending voltage in here, you can totally kill the coupling between the qubits.
And what about next nearest neighbors?
Next near neighbor, you rely on the cleverness of the designer, so they laid out correctly. So there's no knob for it. You just have to engineer it correctly. And usually our indication shows that it's pretty good by design.
So it's just the distance between them, or you need to do something more?
If they are distant and they are not fat objects, then you're good.
OK, thank you.
Well, I mean, they're not perfect, but they have much more difficult other issues, so you don't get to see the cross-couplings. That was a good question. OK. Yes?
So you've got this bunch of resonators, and then you couple them together, and then you get the Hubbard model, right?
Non-linear resonators.
Yeah.
Okay.
So now, what are the regimes of these J's and U's?
Thank
You're
you.
using two, and then so this is all within the first two modes of each resonator.
Okay. Yeah, that's good. So let's just go over there. This H, the way I wrote it, can be from minus 500 to plus 500 megahertz. Okay, maybe since you got to remember three numbers, I should write it down. HI comes from minus 500 or anything you like to plus 500 megahertz. Good? J, all this trick that we discussed about killing it and whatnot, goes from minus 50 to plus 2 megahertz. Okay? So roughly speaking, right? Of course, qubit to qubit is different and whatnot. So the coupling can be this. And U is by design, by the non-linearity, by the capacitance you chose, there's not much you can do. U is about 200 for 200, it depends on qubits, to 250 megahertz. Sorry, this is a minus U. U is minus. Okay, is that answering the question?
Yes.
So we don't have any, okay, maybe I think what the next part of the question was, what the heck, why you just work with 0 and 1? Why don't you just populate half filling and see what happens? We can. So let's say you have 9 qubits, you can put 4 photons and you can ask, and they're gonna end up in one site, I guess, because U is negative. And you can go and wait for it technically and wait for that to see. However, all these numbers coming from constraint that we want to make a quantum computer and two-level systems and the machinery developed for that. So we don't have good readout. If we get to these, remember here, these states are totally physically accessible. You put photons if they want to go to excitation in a site rather than avoiding other sites. Of course, they can do that. But we work really hard to avoid that because we don't have good machinery to read them. Otherwise, if magically you could read them or you have a physics problem, we didn't care about that, that's perfectly feasible. So with all, that's accurate description of the dynamic of the system. But most of our energy goes to avoid this dynamic and confine it to the XY part, XY model, to the hardcore boson limit, just technicality. Am I good? There was a question I missed.
Yeah, I just noticed actually these couplers. There's also one on the left completely and one on the right. So not in the middle of the qubits. What are they for?
To make the design more symmetry and to provide designing criteria. They're not coupling to anything.
Okay.
Well, that's the beauty of this thing. One guy is sitting in computer and drawing parts, so they can easily do that kind of thing to make the design more symmetric.
Yeah. Okay. Fair. Thanks.
Okay. So, Chairman, we have 20 minutes.
Another question?
Yeah, right. We start late. So, okay. Yes.
So it is possible to do single qubit readout in this design, or reading one qubit disturbs also the others, and you have to measure all of them together?
We can do single one. Yeah, we can do single one. More questions? So I can go to the next subject and explain to you why some of them are laughing. Or we can go to the break. I continue tomorrow. I usually ask people's opinion, but then I do what? Huh? You can take like 15 minutes. Okay, that's substantial time. Yeah, but now we know there is no question accumulated toward the end, hopefully. So should we go? Okay, 15 more minutes with me. All right. So this was a almost moment of celebration. now I don't need to look at the slides anymore. That's the beauty. We wrote an article that soon in Thursday, October. We published Thursday, October 23rd, 2019, and it's very highly cited, and we're celebrating it, and this is the object that this group of people made and calibrate, and the next subject of this of the hour of the talk is about discussing that what we did with this team and what this experiment is about. Maybe it's old news, but I felt it's a good opportunity to go over the details and describe what went into this experiment. Is a bit philosophical in a sense that after Shor algorithm and all these beautiful algorithms that were developed for 19s and early 2000s, someone said, is that feasible to do anything with these monstrous platforms that we are making and whatnot? And John Preskill coined the term quantum supremacy. And I know it's in Europe, we have to call it quantum advantage, but so we see how I end up mixing the things. So essentially, can we do anything to show that these are useful? And there is a big philosophical discussion that I get to at the end of the experiment. But there is a good question to ask. Experimentally is a very interesting question to ask. These qubits are faulty, noisy, things break all the time. Is that really possible to outperform a classical computer? It's a serious question to ask. Maybe we're just wasting taxpayers' money. We shouldn't do it. But to do that, well, first you have to come up with an idea, come up with a question, and by default is a very challenging question. You are trying to prove your incapability. You are trying to show you cannot do something, right? In a sense, right? Unlike most algorithm, defines not in terms of a particular problem to solve, but in terms of what classical cannot do. So of course you can fake it. But then you would worry that someone can break it. And that's really has been, in fact, the discussions in the past few years. So you define define a problem very well. You say that actually it's computational value and whatnot. And then you try to solve it in a classical computer. And hopefully there is a complexity theoretic background that backs you up, saying you're fine, but it still is like a black swan. It's like if you haven't seen it, doesn't mean it doesn't exist. So the colleagues of mine who work on this problem were very worried that one day they wake up and there's an article on Archive say that, oh, we could solve it very quickly. It's still some of them missing a slip night because of that, but no, it's real. You don't know there is no algorithm. How can you prove there is no algorithms? You just have to stay worried every day. So I can tell you what it is, and maybe based on understanding it, what it's not. I give you a couple of false examples that has been confused people on the early days of the announcement of the result. You see, if you think that whatever ice in water or something is hard, this is not the way to this business of computer science goes. You have to have a well-defined problem. It has to be. You can compose it in terms of ice and water or whatever you like, but you have to be very precise. What do you want to know about this? Because as soon as you start to defining it, then there is someone tells you a quick trick to calculate what you are specifically excited in. So it has to be well posed. Another thing is maybe a bonus. It has to be programmable, right? You teach your dog, give you a high five. It's not really that's the point. You have to do something that is really can be done in a programmable manner. It's not about a particular action to do. It has to be done over a class of computation, class of algorithms. So we did a random quantum circuits, meaning by default, every quantum circuit can be written, parameterized, and written in given a quantum circuit. So every possible algorithm is included in there. Some of them are simple, some of them are hard, but can be technically math. So is there a existing algorithm that is hard is contained in the group of random quantum circuits. Physicists, you love critical phenomena, you love phase transitions, you get publication out of it, but I have news. That may not be necessarily hard. At least computer scientists are not convinced that anything that you cannot solve is hard. Particularly, you know that close to criticality, there is a universality, there is a scaling at all scale system is acting the same. So most likely, things that you're looking at could be solved much faster than brute force solution. And there is and it has to be studied case by case. So it's just, there is a distinction between a person failing versus there is no algorithm. Let me show you also a historic point that is very, so you really sense how fragile this notion of complexity is. Historically, the one that approved or has the approval of the community for computational complexity is the problem of boson sampling. It's easy to state. You have a network of phase shifter and what is called linear network of interferometer. You shoot a bunch of photons into it, and you say, where do they come out? You put a bunch of detector at the end, and you put photons here, and you shoot there. You just shoot 10 photon in a 50 mode interferometer is already a hard problem. And this is hard because Scott Aronson and his team work it backward. They know a permanent of a matrix is hard to compute. So they cooked up a physics problem, which is the realization of computing the permanent of a matrix. So there was a theorem that says that if permanent of a matrix is easy, then the whole polynomial hierarchy collapse. I don't know what that means, but we want it not to collapse. So then they come up with a physics problem. So if they had it to me, I would say, OK, with photon worked, let me shoot electron in it, get the electron or element of quantum mechanics to interfere, and I ask where the electron came out. That problem is not hard. That's sensitive, that fragile. You get a quantum particle interfere. It matters if you're computing determinant, permanent, which is hard, versus determinant, which is easy. Determinant has a structure that computer scientists know how to simplify it. It's hard for me to solve, but that doesn't count. So this is how fragile a quantum supremacy algorithm and idea could be. We don't know how hard it is. We think it's hard. That's the take-home message in here. OK, what is the celebrated problem that we solve? We put a grid of qubits. Now you guys are qubit masters. You can put them in a 2D grid. This is 6x9 grid of qubits. One of them didn't cooperate. Let me see. OK. And then you apply the sequence of gates to them. These gates are single qubit rotations and entangling gates. Entangling gates are something, a square root of iswap, sorry, iswap if you care, or almost iswap. And you do an operation between them. And at the end of the day, there is a wave function which you originally know is in the product state, 0, 0, 0. And then you evolve it, and you do measurement, as we just discussed, and you get a bit string. It's a 53 long bit string of zeros and one. You repeat this experiment, let's say, 1 million times. It would take about 10 minutes to repeat that. And the claim is that these bit strings are coming from the distribution set by the wave function evolved according to the Schrödinger equation. And we can sample from this distribution faster than any classical computer can do. That is the claim. So the problem is well defined. The gates are written. We give you the gates, say, we can sample the output of this distribution faster than any classical computer, and that's the physics of it. Well, let me see what we going to do next. Well, in the last few minutes, this is not really profound concepts, but so since you get a sense for it, also this is a gift for someone, so don't break it. I need this one really back. But here is actually you got a sense of what it is. Again, it's not such a profound concept that deserves this, but since I had it in my bag, I said maybe I show it to you. You have qubits. In fact, we are very loyal. One qubit is dropout, so this is a space. And in time, you apply a quantum operation to it. And the claim is the wave function that's a product state at this time. When it comes here, is a highly entangled state. Circle this around, please, too. And that's what we can compute faster than anyone else. So the first part of this talk, which maybe I don't get much to it today, is about two notions to establish, the notion of complexity and the notion of fidelity. You know, the water coming out of a fountain is very complex to compute. And that is not sufficient for an experimentalist to generate that. Everyone who sent a grad student to the lab knows they can make a mess very quickly. That's not the point. The point is you have to be on top of that. So not only to create a complex structure, a complex setting, but also to know it with high fidelity. And they come together. And I try to show you our evidences of that in the first part of the talk. And the notion of complexity we get into is by arguing, and it's not complete argument, it's just an argument, that if you have a phase space and you're uniformly exploring it, meaning that you broke all the symmetries of the system, that this phase space is uniformly explored, then there's no way of simplifying the computation, so the entire phase space is needed, therefore there is a chance for it to be complex. But still, you can find structures, of course. You might know about the example of a billiard ball in a stadium, which would get into every place in the stadium if you give it enough time. However, in a circular stadium, there would be regions, depending on initial state, that would be avoided all the times. Okay? So we are going to show that we are using our entire 10 million billion dimensional phase space. Therefore, this computation should be hard. Is an argument. It's not complete. It's not necessary and sufficient. But it's necessary at least, right? And then the notion of complexity and the fidelity. So I feel it's maybe better to stop in here. This is going to go for a while. I can show you the block tomorrow if you want, and we're going to pick it up from here. But maybe there's more questions. Even if it's not important, but you made it very put too many restrictions. Yeah.
The way you constructed the qubits, how scalable is it?
Is it scalable? As far as we know, every step in the design, that's a criteria. If we hit a hard wall in engineering and design, we don't know. Did you ask about the crosstalk? Someone here asked about the second order crosstalk. That kind of thing become important when you make it bigger and explore it. But we don't know. We really have an eye on this. As far as we know, there is not any obvious reason for not into. You have to do engineering things. Even this one I show you, the way we wired it is probably not scalable. But these are anticipated engineering challenges that we are accepting. So if I want to give a simple physics of what is not scalable in there, I wouldn't think, I don't know. But anything could be a roadblock, serious roadblock, we don't know.
But how much could you increase the capacity of qubits in the last 2 years?
Capacity of the
number of qubits you have on a chip.
Well, I think the experiments that I will be talking about would tell you about algorithms we can do. Our approach of doing physics or communicating our advancement is, now I can do this algorithm, now I can do this algorithm. So we are almost, or some would argue, we have passed the threshold. So there was a recent paper of us. We made 3x3 grid of 3x3 surface code, and then we went to 5x5 and said the error has reduced. So it's really going, the error is sufficiently low that by going to bigger scales, we can get hold of errors, and we have probably can put the physical qubits together to make a logical qubits. That's roughly where we are. Oh, Andre.
So I understand the point of view of taking something that's hard, like computing the permanent of even non-interacting bosons, and kind of making it to a physics problem and trying to show that you're better than a classical computer. But I could go the other way and ask, I want to know if the ground state of the Hubble model.
Yes.
How far away are you from a classical computer on that?
The state of the... Yeah, we are, yes, exactly. So as I go over this quantum advantage experiment, you see that we took very specific precautions to be sure we beat a classical computer. We scramble the circuit very fast. We get a very fast scrambling, so entanglement grows very fast. There is no structure in the circuit, and we ask about a global parameter, global variable, which is bit strings. If you take it easy on any of them, then the classical computer can catch up with you. So what we do with classical computers in the algorithms, you could care, let's say, discrete time crystal, let's say Majorana Majorana is not even interacting or whatnot. No, laptop is still catching up with us very quickly. But maybe you should wait for the end of tomorrow toward the end, I would give examples. But truth to be told is all at the level of laptop. Yeah. But you know, if a physicist define a problem, say, hey, I'm interested in the quench dynamic in the Bose-Hubbard, there you go, we can do it quickly.
Ground state of the Hubbard model would be nice.
Huh?
The ground state of the Hubbard model would be nice.
Quench dynamics, yeah. Well, okay, so you know that when you're trying to anneal to it, yeah, you need time, and then time needs coherence, which we don't have.